Well, first of all, let me thank the organizers for giving me the opportunity to talk here. So I will follow up on the talk by Niels, and I will basically supersymmetrize part of what Niels said. So I will talk about non-Lorentzian supergravity. And in order to motivate why this is an interesting thing to do, let me just start by flashing a partial list of some of the things that Niels mentioned, some of the applications of non-Lorentzian geometry that Niels mentioned. So Niels basically said that non-Lorentzian geometry is a really useful tool if you want to describe systems that take place in some kind of non- or ultra-relativistic regimes. It has been applied to like holography, construction of effective field theories in strongly coupled condensed matter systems, non-relativistic fluids, large and small C expansions of general relativity. Recently also in the context of celestial holography and the connection with Caroline physics. And the one thing that I would like to highlight, because it will be one of the motivations for this kind of work, is this non-relativistic string theory here that Niels mentioned, this kind of limit of relativistic string theory that was invented by Gomes and Oguri and also by Danielson, Goyosi and Kruczynski in the early 2000s. As Niels mentioned, it's essentially kind of a subtle extremal limit. It's in fact an infinite tension limit of relativistic string theory where you assume that your string is compactified. And it's characterized by non-relativistic dispersion relations. So the spectrum of string excitations has non-relativistic dispersion relations, and they interact via some kind of Newtonian gravitational interactions. Now, when I mention the word string theory, then it's of course very obvious to think that you should add super to it. You should consider superstring theory. So you can also consider non-relativistic superstrings. And then, of course, there are natural questions that pop up. For instance, what is the analog of supergravity in these non-Lorentzian superstring theories, in these non-relativistic superstring theories? So these non-relativistic superstring theories exist. Thus, there exists something like non-relativistic supergravity that plays a similar role as relativistic supergravity plays for relativistic string theory. There are other reasons why you might be interested in non-Lorentzian supergravity or non-Lorentzian supersymmetric curved spacetimes. For instance, you might want to use non-Lorentzian supergravity to construct supersymmetric field theories on curved non-Lorentzian backgrounds. You might be able to try to see whether you can localization techniques to, for instance, compute certain observables in an exact manner in such theories. Recently, there's also been some interest in supersymmetric condensed matter field theories. In particular, there was a paper quite recently by Gromov et al., where they consider some effective theory for some effective theory in some gapless fractional quantum Hall state. And they, basically conjecture that it should be described by some supergravity theory. And it's not your standard supergravity theory. It is really some kind of non-relativistic supergravity theory. Now, as soon as you start thinking about the details of what it would mean to merge supersymmetry with non-Lorentzian geometry, or to what it would mean to construct non-Lorentzian supergravity, then you quickly find that it's quite subtle, it's quite non-trivial, and there's also quite interesting puzzles that appear. There's a couple of things that work quite differently from standard ordinary supergravity. The good news is that in recent years we've developed a lot of technology concerning non-Lorentzian geometry. Many of these questions have now become accessible. So what I will do in this talk is kind of give you an overview, a short overview of what has been done on non-Lorentzian supergravity. And so from the start, I can say that the only examples that have been considered so far are cases in which the underlying geometry is what I call p-brane Newton-Cartan geometry. That includes the Newton-Cartan geometry that Niels discussed, and it also includes the stringy Newton-Cartan geometries. It's in fact a generalization to generic p-branes. I will explain what this p-brane Newton-Cartan geometry is in a bit more detail. I will focus on the aspects of it that are important for supergravity. Then I will briefly say something about the methods that we used so far to construct non-Lorentzian supergravity theories, and then I will give two examples that are both related to non-relativistic string theory. The first example is a minimal supergravity theory in 10 dimensions that is relevant for non-relativistic string theory. And the second example that we are currently trying to work out deals with a non-relativistic version of 11-dimensional supergravity. And then I will end with some outlook and basically a huge list of things to do and things to consider. Okay, let me start by giving a bit more details about these p-brane Newton-Cartan theories. So these p-brane Newton-Cartan theories, well, they are essentially the spacetimes that non-relativistic particles, strings, and branes move in. And you should see them as a limit of Lorentzian geometry, but it's not the standard C to infinity limit, but you effectively take the speed of light only to infinity in directions transverse to the p-brane. Basically, if you think about the local light cone, you should really think of the C to infinity limit as a limit in which you send C to infinity only in the transverse directions. So part of a local light cone flattens out, but it's only in the transverse directions that the light cone opens up. Along the world volume directions, along longitudinal directions to a p-brane, spacetime still is entirely Minkowskian and the speed of light stays finite. Now, to describe the geometry in more detail, since I do supergravity, I will need a Vielbein formulation, so I can essentially describe the Vielbein formulation of p-brane Newton-Cartan geometry in analogy to how you do it in Lorentzian geometry. Unfortunately, I see that the indices got a bit messed up by the projection. So in standard Lorentzian geometry, you have an invertible Vielbein that transforms under local Lorentz rotations in the fundamental representation. And the first thing that you should do is give the analog of local Lorentz transformations for these p-brane Newton-Cartan geometries. And the way in which you do it is you take the d-dimensional index A hat, the d-dimensional Lorentz index A hat, and you split it in two subsets. One that I denote by capital A, that takes p plus 1 values, and then the one that I call small a, that takes the remaining d minus p minus 1 values. The capital A I will call longitudinal, and the small a I will call transversal. Once you've done the splitting of the indices, you can replace the local Lorentz transformations by a group that's, unfortunately the projection is really messing my slides up quite badly. So it's essentially a semi-direct product of boosts with a direct product of SO1, P and SOD minus P minus 1. So the SO1, P factor that is basically that mixes the longitudinal directions, so that's just an SO1, P Lorentz group that mixes the longitudinal directions. Then you have transversal rotations that mix the transversal directions, and then the boosts, they send transversal directions to longitudinal ones, but not vice versa. You can then introduce the Vielbein structure. To do it, you introduce two Vielbein, one that I call a longitudinal Vielbein and one that I call transversal. And they transform under the structure group that I've just shown in the fundamental representation, essentially. So tau only mixes to itself according to longitudinal Lorentz transformations. The E transforms into itself under transversal rotations. And moreover, it shifts to the tau under boosts. Once you have these Vielbein, you can introduce dual frame fields as well, just in the standard way. And then using these Vielbein by squaring them appropriately, you can introduce two metrics that are degenerate, one of rank p plus 1, that is a longitudinal Lorentzian metric, and then one co-metric of rank d minus p minus 1 that is just a standard Euclidean metric. As Niels also mentioned, you need an extra ingredient. It turns out that you also need to introduce a p plus 1 form that transforms under boosts to the E's and the taus. That's an object that will couple to non-relativistic p-branes. So in the p equals 0 case, for instance, this is the central charge gauge field mu that Niels showed. In the p equals 1 case, that's a stringy case, then it's really the b mu field that Niels, or the m mu field that Niels showed. What this field does is it does actually something very physical. It takes care of conservation of brane tension. That's something that you want to impose separately in non-relativistic theories. So for instance, in the case of p equals 0, this the case of a non-relativistic particle, there is just an ordinary gauge field that couples to the neutral current that is associated to the symmetry that implements conservation of mass, and conservation of mass is really something that you want to implement separately in non-relativistic theories. So the picture that you should have in mind, that I can draw easily, that's for p equals 0 and p equals 1, is that locally these geometries look something like this. So for instance, for the p equals 0 case, you have space-time that's locally you can slice up in spatial slices, and then there's a time direction, and moreover there's an extra mu field to which massive particles couple. And similarly for the p equals 1 case, that's a stringy case. Locally, there's a notion of transverse space to the string, and then there are some kind of world volume directions that are singled out, and there's an extra two-form field that couples to a string according in the standard way with a Bezold-Minot term. That gives you the metric structure of the geometry. You should then also, of course, give the connection structure. You can introduce spin connections in the Vielbein formulation, in analogy to how you do it in Lorentzian geometry. So in Lorentzian geometry, you introduce a spin connection that satisfies the first Cartan structure equations. In p-brane Newton-Cartan geometry, you will introduce 3 spin connections that are associated to each of these factors of the structure group, and you will just write p-brane first Cartan structure equations that are really very analogous to the standard first Cartan structure equations in Lorentzian geometry. So you just take like properly covariantized curls of the Vielbein, and since the B fields, the p plus 1 form fields also transforms under boost, you can also use it to introduce the first Cartan structure equation. There are 2 qualitative differences with standard Lorentzian geometry that are kind of related. One difference is that these first Cartan structure equations do not determine the spin connections uniquely in terms of the Vielbein and torsion tensor components, at least not for p bigger or equal than 1. So these p-brane first Cartan structure equations, they don't single out a unique metric compatible connection, but a whole family of metric compatible connections. And then more important for my talk is the second related difference. That is that if you look carefully at these first Cartan structure equations, then you see that some of them do not contain spin connection components. In particular, you can take, for instance, suitable projections of the first Cartan structure, the first Cartan structure equation along transversal and longitudinal directions, and you will see that for some of these projections, the spin connection omega mu AB drops out. That is expressed mathematically by saying that p-brane Newton-Cartan geometry has intrinsic torsion. And this intrinsic torsion, these are just the torsion tensor components that appear in these first Cartan structure equations that do not contain spin connections. Why is that important? Well, it leads to a very qualitative difference with standard Lorentzian geometry. In standard Lorentzian geometry, if you impose constraints on the torsion, then it just means that you choose a particular connection. Here, if you impose constraints on these intrinsic torsion tensor components, then it amounts to choosing particular connections, but something more as well. Namely, it amounts to imposing geometric constraints. So you see that if you put some of these intrinsic torsion tensor components equal to 0, then you really get constraints on the curl of this longitudinal Vielbein, and these are really kind of constraints, differential constraints on the metric structure. That's very different from standard Lorentzian geometry. You can classify all these constraints for generic p-brane Newton-Cartan geometries. You can give a geometric interpretation. I'll just single out 2 of them. The first one is essentially saying that this one here is entirely equal to 0. That is the p-brane analog of this twistless torsional constraints that Niels showed. So that basically means that your manifold can be foliated in d minus p minus 1 dimensional transversal leaves. If you put all intrinsic torsion tensor components equal to 0, it turns out that there's a notion of absolute world volume. In the p equal to 0 case, that just translates to saying that there's a notion of absolute time. That's the standard Newtonian absolute time notion. So in this geometric framework, this is implemented by imposing intrinsic torsion constraints. Okay, so that's what I need concerning the geometry, and now I can start discussing more about supergravity. So the central question that we basically want to ask ourselves is always like, is non-Lorentzian geometry compatible with supersymmetry? Can you construct something that can be called non-Lorentzian supergravity, and what is its structure? So as I said, so far this has mostly been done for the cases in which the underlying geometry is one of these p-brane Newton-Cartan geometries. And there are essentially two types of methods that you can use to construct non-Lorentzian supergravities. I call them intrinsic and extrinsic. By intrinsic, I just mean direct construction starting from something non-relativistic. You know some non-relativistic superalgebra, you know representations and so on, then you can try to use that to directly construct non-Lorentzian supergravity theories. That method has a drawback, namely that there's not so much known in general about non-Lorentzian superalgebras and their representations, so there's still quite a lot of work that needs to be done there. Nevertheless, it has been applied in the simpler setting of 3 space-time dimensions for p equals 0, so for like these particle Newton-Cartan geometries. Essentially, what has been done there is that people have come up with a whole zoo of non-relativistic superalgebras that you can gauge to construct non-relativistic supergravity theories in 3 dimensions. The second method that I will illustrate in a minute in this talk, that I call extrinsic because it refers to some kind of relativistic counterparts. And it's essentially starting from some relativistic supergravity theory and then using that to construct something non-relativistic or something non-Lorentzian, either by doing a null reduction, as Niels mentioned, or by taking limits, non- or ultra-relativistic limits. That has been used so far in d equals 10, and currently we're also using it in d equals 11, and that's what I will explain next. The drawback of that is that it can be rather subtle, and part of the aim of the next section is to show some of these subtleties that appear. It's also not really sure whether this really exhausts all possibilities, so it might be possible that there exists non-relativistic or ultra-relativistic supergravity theories that you cannot obtain easily from a limit. That is entirely possible. Let me illustrate this limit procedure in the case of minimal supergravity in 10 dimensions. So there the starting point is n equals 1, 0 supergravity in 10 dimensions with field contents the Vielbein, the Kauper-Amont 2 form, a dilaton, and then a gravitino and a dilatino that are left and right-handed Majorana-Weil spinors respectively. And then what you do to take the non-relativistic limit is, well, you start again by doing the splitting of the flat index A hat in 2 longitudinal values that I will denote either by 0 or 1 or in light cone notation by plus and minus, and then transversal directions. And then what you do in order to take the limit is first you propose an invertible field redefinition and also a redefinition of all the parameters, Lorentz transformation parameters, supersymmetry parameters, etc. And this field redefinition goes with a parameter that you introduce that I call C, that is morally speaking the speed of light. It's really just a formal expansion parameter at this point. So what you do is you rescale the longitudinal components of the Vielbein C, while the transversal components you leave untouched. For the fermions, you split them up in 2 representations, in 2 separate representations under the transversal rotations. I call them plus and minus, and these you rescale differently with factors of C. And then the funny one, that's the expansion ansatz you take for the B fields. So you say that the B field has a C to the 0 term that is just another 2 form small b. And then there's a C squared term that is essentially a wedge product of the 2 taus. That is actually motivated by non-relativistic string theory because this is the ansatz that you take in order to obtain the non-relativistic string action, the curve space analog of the Gomes-Okori non-relativistic string action from the Nambu-Goto or Polyakov relativistic string action. So this is basically what motivates us to take this ansatz for B. What you then do in order to take the limit is essentially you plug in this ansatz in every quantity that you want to consider. Action, transformation rules, equations of motion. You expand in powers of 1 over c squared, and the limit consists of taking the leading order term in such an expansion, ideally. So if you do it, for instance, for the bosonic transformation rules, then you see that generically you get a term at order c to the 0, and then a term at order c to the minus 2. So the limit just consists of dropping the c to the minus 2 terms. And you see that for the tau, the E, and the B fields, you essentially regain these structure group transformations that define what Newton-Cartan geometry is. So these transformation rules under longitudinal Lorentz transformations, transversal rotations, and Galilean boosts. For the fermions, you find that under boosts, one goes to the other, but not vice versa. That's classic non-relativistic behavior. And one thing that is also very peculiar is that there's an extra symmetry that appears that you only see when you really study the equations of motion and the action, and that's the dilatation symmetry. That does not really come from a limit of relativistic transformation rules, but it's just a fact of life that after you've taken the limits, then it turns out that the theory exhibits an extra emergent dilatation symmetry. You can expand the action as well. Generically, generically, you expect that there would be a term at order c squared because some of the terms in the action start at order c squared. However, it turns out, and this is really due to this B field redefinition, that there are some cancellations that happen that ensure that this term at order c squared vanishes exactly. So the expansion of the action starts at order S0, starts at order c to the 0, and you would then say that the limit of the action is given by this S0. It's by default invariant under these zeroth order bosonic transformation rules. So far, so good. However, when you look at the supersymmetry transformation rules, then it becomes a bit more subtle because the expansion of the supersymmetry transformation rules starts at order c squared. Then it has a term at order c to the 0 and a term at order c to the minus 2. So naively, you would say that the limit is given by the leading order term. So naively, you would identify the non-relativistic supersymmetries with this c squared term. But that cannot be true. If you look carefully at the exact expressions, you see that they can never give rise to non-relativistic supersymmetry. In fact, if you look at the terms at order c to the 0, then you see that these are really the transformation rules that you want that can constitute non-relativistic supersymmetry. So there is this divergent part in the supersymmetry transformation rules that you have to deal with. And you can actually deal with it by imposing intrinsic torsion constraints. And this is something that is very typical in constructing supergravity theories. It also happened in these three-dimensional examples that we constructed using intrinsic methods. You always have to impose some sort of torsion constraints. And here you see it happening also. You see it arising from the limits because you have supersymmetry transformation rules that diverge. So in this case, it's actually quite nice. It turns out that you have to more or less constrain half of the intrinsic torsion to be equal to 0. And the nice thing is that this is a supersymmetric thing to do. These constraints are invariant under the zeroth order supersymmetry transformation rules. So usually when you impose constraints, you have to do it in such a way that it's compatible with supersymmetry. So you have to vary the constraints and then impose the variation of the constraints again as constraints, and then you have to vary that again. And again, you might get new constraints. You might get a whole tower of constraints that you need to impose in order to have compatibility with supersymmetry. Here it turns out that it's very easy. You just have to impose these constraints and you're done. So I mentioned this dilatation symmetry. You also get some kind of supersymmetric analog of that. It turns out that there are emergent fermionic shift symmetries. There's some kind of a superconformal symmetry appearing. They are really ordinary shift symmetries. They take the form of like Stuckelberg symmetries. So that kind of means that with respect to the original relativistic starting multiplets, there's some kind of multiplet shortening going on here. There are some components of the multiplets that you can get rid of in a trivial manner just by gauge fixing these fermionic shift symmetries. If you examine the equations of motion, you can also take the limits of the equation of motion. That's a bit subtle, but it can be done. And if you examine them carefully, then you see that it's basically, it gives you a diffeomorphism covariant version of the Laplace equation, where the role of the Newton potential is played by the longitudinal components of the two form, the Kalpramont two form. So that plays the role of the non-relativistic Newton potential. And the bosonic part of these equations of motion also exactly corresponds to the beta functions of non-relativistic string theory. Those have been calculated by Gomis, O, and Jan and Yu. And we can basically reproduce this by this limit procedure from the well, in essence, gravity equations, or in this case, the supergravity equations of motion. To finish, let me briefly say something about the 11-dimensional case. You can deal with it in very much the same manner. So again, you can take the limit in a very similar way. You can propose these kind of field definitions that involve parameter C. In this case, you have a 3 form, but it's a very analogous ansatz that you take as the one for the 2 form that I've shown. In this case, not all the divergences in the action are cancelled by this ansatz. It turns out that there are some remaining divergences, but you can regulate them, you can take care of them because they take the form of a perfect square, and then essentially you can use a Hubbard-Stratonovich transformation to turn a C cube term, a divergent C cube term in the action, into a C to the 0 and a C to the -3 term. So in this way you can regulate this limit procedure. One difference with the 10-dimensional case is that, again, you get emergent shift symmetries, and again, you get divergences in the supersymmetry transformation rules that you can deal with by imposing constraints. But here, in this case, life is not so nice as in 10 dimensions. These constraints are not supersymmetric. So again, you have to impose intrinsic torsion constraints. In this case, you, in fact, have to impose that most of the intrinsic torsion is equal to 0. These constraints are not supersymmetric, so you have to vary them and impose their variation as a constraint. You get new constraints whose variation you have to impose as a constraint, etc., etc. So you get a whole tower of extra constraints that constrain some of the curvatures of the manifold. But it can be done. One thing that I want to mention also is that this theory actually has a non-trivial supersymmetric solution that has been proposed recently by Lambert and Smith. So what Lambert and Smith did was they considered a particular scaling limit of ABGM theory that is non-trivial in the sense that it describes motion on the moduli space of the Hitchin equations. And so they conjectured that there should exist a limit of the standard relativistic M2 brane solution, particular scaling limit of the standard M2 brane solution, that is fully supersymmetric, or at least whose near horizon limit is fully supersymmetric, and that we indeed reproduce. So we can check that this solution is indeed a solution of our equations of motion, and that it's fully supersymmetric. Okay, so let me finish. Well, I've basically tried to argue that non-Lorentzian geometry and supersymmetry can be made compatible. It's slightly non-trivial. There are interesting structures that appear that need to be explored. There's a whole list of things to do, both from a technical point of view. So far, we've done this on a case-by-case basis, just constructing examples in 3 dimensions because it was easy. We could do the cheap thing, so to say. In 10 dimensions, we managed to figure out how the limit works. But it's fair to say that what we've done so far is not very systematic, and we really need analogs of standard techniques like superconformal tensor calculus, rheonomic approach, superspace techniques to do. We need to adapt them to also construct non-Lorentzian supergravities. One can also start looking at other types of non-Lorentzian supergravity. One thing that is very interesting that it would be to look at solutions. So I mentioned these Lambert-Smith solutions. It would be very interesting to look at, to really explore the solution space of these non-Lorentzian supergravity theories and kind of try to see whether they can act as duals of various decoupling or scaling limits of supersymmetric field theories that one can consider. Another interesting thing to do would be to use this formalism to construct supersymmetric field theories on curved non-Lorentzian backgrounds and to see whether some of these theories can be amenable to localization techniques. And as a take-home message, well, I can just say that experience has taught us that relativistic supergravity always seems to know more than meets the eye at first sight. So it really contains the seeds of many important lessons that we've learned for quantum gravity and non-perturbative QFT. And in recent years, we've really developed tools and technology that allow us to check whether non-Lorentzian supergravity might hold similar lessons for their non- and ultrarelativistic counterparts.
Questions?
was just a question about the solutions, because you mentioned that to have supersymmetry you need certain torsion constraints.
Yeah.
So have you checked, or can you see in some, let's say, solitonic solutions of relativistic supergravity or string theory that after the limit automatically, after the non-relativistic limit, automatically those solutions satisfy those constraints?
Yeah, we haven't done it in full detail. So the only solutions that we checked so far are this Lambert-Smith solution, and then of course the standard M2 brane solution. They satisfy these torsion constraints, but yeah, I cannot make any general statement at this point.
But would you expect that there's sort of a one-to-one correspondence, or
yeah,
could it be new? Well, do you have any expectations?
I would expect if you manage to take the limit in the correct way, but that's sometimes a bit subtle for solutions. I would expect that it works, but at the moment I cannot make a very general statement. I have to say.
You want to make a comment? Just a comment, and then
It wouldn't be inconsistent if it doesn't work, no? It just means that that solution after the limit is not supersymmetric.
Yes, yeah, that's true, yes.
Did anyone try to approach these supergravities, non-relativistic supergravities, from superspace side?
No, not so far. Not. No, that would be very interesting to do. It's really so. I have to say, this tower of constraints that we get, that really it really cries out for supersymmetry. You get a whole multiplet of constraints, and this is really something that cries out for superspace. So it will be really useful and handy to have a superspace formulation. So far, we have not done it.
Yeah, thanks.
In the outlook, there is some point about dualities. So I was wondering, have people studied toroidal compactifications in those supergravities, and is there some equivalent of T or U dualities?
Yeah, that's a slightly subtle. It's more subtle than in the relativistic case, as Niels also mentioned at the end of his talk. So what you can do is, in this non-relativistic string theory, you have two distinguished directions. So you have difference between longitudinal and transversal directions. So you can do T-duality along both of them. If you do it along a transversal direction, you find that non-relativistic string theory maps to non-relativistic string theory. If you do it along a longitudinal direction, you actually find that it maps to the DLCQ of string theory. So you really find that it maps to relativistic string theory on a background with a null-killing vector. So that's slightly subtle. You can indeed start considering various compactifications and so on, and try to build up a whole web of T-dualities. You can ask yourself the question whether, so far we've only considered P equals 0 and P equals 1 supergravities, but it's natural to think that that one can try to construct supergravities for arbitrary values of P. You can really ask yourself the question, does there exist a whole web of dualities that relates all of these to each other? So far, these things have not been explored that much.
Okay, one last question.
Yeah, maybe it's related to what you have said. In the relativistic theory, we have the universal space-time with a certain geometry on which all these dynamical objects live, like particles, strings, branes. Here, it's as far as I understood, each dynamical object has its own geometry where it can live. Mm-hmm. So the question is what it means conceptually. For example, if you take the intersection of a string with some p-brane, what kind of geometry? Can it coexist, for example, in more complicated cases?
Well, that's a good question. So as I said, so far these things have not been explored that much yet, unfortunately. My personal expectation is that it should be possible to still find something that you could call a p-brane solution or a remnant of a p-brane solution in, for instance, like a P equals 1 stringy supergravity theory, and vice versa. If you have like various p-brane supergravity theories, you should be able to find like all the other, or remnants of all the other branes as solutions. But again, so far, we have not really explored this in full detail.
Okay, let's thank Jan for his talk.